Hello everyone, my name is Anshuman S222137855, and welcome back to my tutorials. In this video, we are going to be diving into the world of asymptotic notations. This topic is crucial for understanding the efficiency of algorithms because when we analyze algorithms, we often discuss their time complexity using asymptotic notations. In today's tutorial, we'll cover the basics, and these insights will be valuable for your assessments or like our on-track task for this week and onwards. Before we get started, let's take a look at what actually asymptotic notations mean. Asymptotic notation is a mathematical way of representing the time complexity of an algorithm. It's a tool for analyzing the performance of algorithms without actually executing them. We often perform asymptotic analysis to understand how the running time of an algorithm grows as the input size increases. Now, to calculate the time without execution, we focus on how many times a statement is executed, known as iteration frequency, which is also covered in our assignment for this week. This leads us to concepts of big O, big omega, and theta notations, among others. Let's start with the big O. Now, big O notation is like setting an upper bound on the growth rate of an algorithm running time, or the worst case scenario of an algorithm. We represent it as Fn equals to O of Gn, where Fn is the time complexity of our algorithm and Gn is a function that serves as the upper limit. Now, the key is to choose Gn such that its smallest function that's still bound to the growth of Fn. So for example, if we have a function Fn equals to 2n squared plus n, and we want to represent it in terms of big O, we have to choose Gn as c times, or a constant, times n squared. This choice ensures that the algorithm's time complexity grows at most quadratically with the input size and is the closest upper bound limit. So the upper bound limits could have been n cubed, n to the power 4, n factorial, but since in big O we choose the closest upper bound, we have to take n squared. Now, the upper limit is governed by a constant term c, ensuring Fn is less than or equal to c times Gn for all values greater than or equal to the chosen k. Choosing c and k wisely is crucial for accurate representation, so if Fn is 2n squared plus n, we have to choose the c's such that will be greater than 2n squared plus n indefinitely. So in this case, I've chosen 3. So 3 times n squared will always be greater than 2 times n squared plus n. And you can try this out as well, but it's very important to choose constants properly. For big O or big omega notation, it is the exact opposite of big O, where big O being the worst case scenario and big omega being the best case scenario, or the lower bound of an algorithm's growth rate. We write it as Fn equals to omega Gn. This time we choose Gn such that Fn is always greater than or equal to c times Gn for some constant c. And as mentioned in big O, it has to be the opposite for big omega. So instead of choosing this constant so that it is greater than Fn, it has to be less than Fn. So in this case, I've chosen 2. So 2 times n squared will always be less than 2 times n squared plus n. And this makes sure that our algorithm's time complexity is always consistent with its notation. Now for theta notations, they combine elements of both big O and big O omega. It represents an average case scenario indicating that Fn grows at a similar rate as Gn, or we can write it down as in such way, where C1 times Gn is less than or equal to Fn, which is less than or equal to C2 times Gn. Now this holds true with the way we looked at it in the previous examples, where if we take 2 for C1, or 2 for C1 and 3 for C2, this will hold true no matter what in all cases. And since it provides a more precise understanding of an algorithm's growth rate by considering both the best and worst case scenario, it is also a very important factor to consider. Now, there's also, other than these, the literal and little omega notations. Literal and little omega notations are variations where less than and greater than are not used, or less than equal to and greater than equal to are not used. So it's basically the same thing, just without the equals to. So it has to be less than, or it has to be greater than. And these notations are used when you want to specify upper or lower bound limits without the possibility of being equal. And to conclude, these asymptotic notations play a crucial role in analyzing algorithm efficiency. Big O, big omega, and theta notations provide insights into the worst case, best case, and average case scenarios. And little o and little omega notations offer more specific bounds without including equality. And that's all for this tutorial. Thank you for watching.